All right.
But I think I'm gonna have to update now. I know I can do it.
So far, in our math careers, we've been working with functions, what we call explicit functions. Where we have something like y equals f of x. We've done a lot of work with functions like that. And we call that an explicit function. Y is explicitly a function of x. We can list out y equals natural log of x minus 1. We know exactly how to get y from a value of x. What we're going to do in Chapter 10 is talk about parametric equations. And what happens with parametric, I'll say not functions, equations, because we have a pair of functions. Each variable is a function of a third variable. And we call the third variable the parameter. And our probably the most common parameter for what we've done is time, or for what you've done in the past is time. So what we have is something like we're going to say x equals f of t and y equals g of t. So we have some function that gives us our x coordinate, some function that gives us our y coordinate, and t is the parameter. And for some things that we'll do, we will choose the parameter in a way that makes things work out nicely. So this is what we call a set of parametric equations. Probably the classic example of a set of parametric equations is projectile motion. So we have projectile motion, x equals v0t plus x0. And then y is 1/2, and I'm going to say v0x, because we're going in the x direction. Y equals 1/2 a t squared plus v0y t plus y0. And our acceleration usually is acceleration due to gravity. So that would be, this is a set of parametric equations, and our parameter is time. We plug in any value of time, and we know the x coordinate and the y coordinate. We can plot those points, and we get a graph of the motion versus time, but we plot it in an xy coordinate grid. When we plot the path of a parametric equation, we call that path is a plane curve. So that's the terminology we use for the graph of the parametric equations. All right, so what we're mostly interested in today is how we visualize parametric equations. So we're interested in the visualization, and just to be one little piece of technicality, we call the set of points x and y. We call that the graph. Technically, the plane curve is the set of parametric equations, the graph, along with the set of parametric equations is the plane curve. So this is a little technicality. We kind of use them interchangeably. All right. So the first thing that we're going to do is talk about, if we have a set of parametric equations, how do we get it into a form that might be more familiar? So we want to talk about eliminating the parameter. Limiting?
Getting rid of the limit?
Yeah. I told Miss Felkner last night at conferences, said I used to think that Calc 3 maybe was the hardest class at school, but from what I hear, it's her class.
I think you're going to have to talk to Mainland next time.
Yeah, I'll have to talk to Mr. Mainland too.
Calc is a different kind of, but it's easy to make easy. Like, you just gotta work at it. Like, there's nothing.
The test on the same day as this.
There's nothing you can do in Miss Felkner's class to make it easier. There's stuff you can do in calculus to make that easier.
Right. That I have a math professor quote that says that math is nice because in history there's not a formula to remember the dates that things happen. All right, so when we eliminate the parameter, what we're doing is we start with our equations. So we have our parametric equations. We are going to solve. Now, let me ask. I can't remember, because some years in pre-calc we have time to talk about parametric equations. Other years we don't. When we did pre-calc, did we talk about parametric equations? Okay, so we did a little bit of this in pre-calc. We want to solve for the parameter in one equation. Now, this is not what we do every single time. This is more of kind of a rule of thumb. Solve for the parameter in one equation, and then we substitute. And when we substitute, we have to, once we make our substitution, we adjust the domain. Because the parameter of the domain is then going to determine, or the domain of the parameter is then going to determine the domain of our function, our explicit function. So let's look at a couple of examples where we eliminate the parameter. Start with an easy one. So we want to eliminate the parameter. See if I can spell right correctly. Eliminate the parameter. And sketch the graph. So I'm going to say x equals t minus 1 and y equals, y equals, that's what I wanted, 2t squared minus 4t plus 1. And we're doing this on 0 less than or equal to t less than or equal to 2. So before we even eliminate the parameter, what kind of graph do we think this is going to be? It's going to be some kind of parabola, right? Because we have a linear equation in the x-coordinate and a quadratic expression in the y-coordinate. So there's going to be some kind of quadratic relationship between the two. So which equation should we solve? X. Let's make our lives easier for a second here. So I'm going to say from the first equation, I get that t equals x plus 1, and then we substitute. So we get y equals 2x plus 1 squared minus 4x plus 1 plus 1. And we simplify that a little bit, do some algebra. 2x squared minus 1.
I'm gonna need a minute.
So we square this, distribute, combine like terms.
Oh, I got it.
Okay. Sometimes I make arithmetic errors. I make spelling errors more often.
Yeah.
And now we're going to adjust our domain. 0 is less than t, less than or equal to 2. Well, that's going to imply that -1 is less than or equal to x, less than or equal to 1. So if we look at our x coordinate, we substitute in 0, we get -1. We substitute in 2, we get positive 1. So our domain is from -1 to 1 in our x coordinate. And if we sketch a quick graph, we get something like this. I'm just putting some points here. We get a nice parabola. So we go from -1, 1 to 1, 1. And the other thing that happens with a set of parametric equations, and this is 0, -1. When we parameterize an equation, or when we have parametric equations, our curve has an orientation. As our parameter increases, we travel a specific direction on the graph. We call that the orientation. As t increases, we want to know which direction we travel on the graph, because depending on the parameterization, we could travel left to right or right to left. So as t increases, so when t is 0, x is -1. And when t is 2, x is 1. So we're traveling along the graph as t increases. We're traveling along the graph in that direction. So if you graph this in your calculator in parametric mode, your calculator would graph like so. So we would say this has left to right orientation. We call that the orientation. And as we move forward, there will be things that we do in Calc 3 where we want to parameterize so that we have a specific orientation, or we'll be required to have a specific orientation. So you need to parameterize appropriately so you travel in the right direction on your graph. And we call that direction you travel the orientation. As our parameter increases, which direction do you go? All right, let's look at another one where it's a little less straightforward than solving for one of the variables and substituting. All right, so we want to, usually we're going to eliminate the parameter so we can visualize what the curve looks like, to sketch the graph. So we want to sketch the curve represented by x equals 5 sine theta, y equals 3 cosine theta, from 0 less than or equal to theta less than or equal to 2 pi. So this one, if you solve the equation for solve one of the equations for the parameter, you get the inverse sine or inverse cosine, and that is really, really messy. Any other ideas what we might do here?
Make a triangle.
We're kind of along the in the right direction.
We need to make a line.
You could, and I think you would get there by making a triangle. Well, what if I do this?
Yeah, that's the same thing.
Just making a
Kevin,
what lovely relationship do we know between sine theta and cosine theta? Sine squared theta plus cosine squared theta equals 1. So that tells me that x over 5 squared plus y over 3 squared equals 1. And I'll write this maybe in a more familiar form. Whoops, 25.
Oh, sorry, Connor.
And what is that? An ellipse. So there's our conic section that we already know about. Major axis along the x-axis or y-axis? X-axis. How long is the major axis? 5. And the minor axis? 3. Nice. There's my...
Why is white cute?
Someone teach me that.
Because there's a 3 here. Whoops. See, and I did it again. Doesn't that make sense? There's a 3 there, so it's cubed.
It's like, why is white cubed and then you put cube again?
Oh, yeah. All right, so there's my ellipse. The major axis on the x-axis. So this is going to be 5, 0, negative 5, 0, 0, 3, and 0, negative 3. All right, and now let's find the orientation as theta increases. So the way I usually look at this is, let's just look at one of the coordinates. When theta is 0, what is x? Sine of 0? 0? When theta is, let's just go to pi over 2. What is? 1. So as we go to pi over 2, as the parameter is increasing, I'm going from 0 to 1 at theta equals pi. No, wait, x is not 1. Sine theta is 1. X is 5. There we go. So we're moving that direction on the curve. So we go from 0, x equals 0, as when theta is 0, to when theta is pi over 2, we go to x equals 5. So we're moving clockwise around that curve. How, if we wanted our orientation counterclockwise, how could we? What would we change around?
Switch it. Make it switch the alligators. To alligators?
If we wanted to have a parametric equation of an ellipse, but we wanted the orientation to be counterclockwise.
Flip sine and cosine.
Let's change sine and cosine. So our x coordinate would be starting at 5 and going to 0. Yeah, Kyle.
I'm really confused on that.
What did I tell you?
Orientation. So what I did was I started with when theta is 0. I plugged that in here. So when theta is 0, y is sine of 0 is 0. So x is 0. So at my x, I'm at 0, 5 on or 0, 3 on my graph. When theta is pi over 2, so we're increasing. Sine of pi over 2 is 1. So x is 5. So we go from here to here between theta equals 0 to theta equals pi over 2. So as the parameter is increasing, I'm going that direction. If you went to pi, then sine of pi is 0. So we'd be back to here. Okay? All right, so we say this has clockwise orientation. And depending on how we parameterize the curve, we could make it counterclockwise as well. We could switch the sine and the cosine around, and we get a counterclockwise orientation. All right. So we eliminate the parameter mainly to help with sketching the curve. Sometimes we want to represent an explicit function, y equals f of x, as a set of parametric equations. So there will be times, and it might be hard to believe now, where it's going to be more beneficial to represent x squared over 25 plus y squared over 9 equals 1 as x equals 5 sine theta and y equals 3 cosine theta. So for stuff that we'll do in the future, it will be nicer to work with these equations than this equation. So what we want to do next is just talk about how we might parameterize some curves. Mm-hmm.
Regular.
All right. So we're just going to do a few examples of this. This is not particularly, the concept's not particularly difficult. Sometimes we will, in the future, we will pick a particular parameter. For some things that we do, it's going to be beneficial to parameterize in terms of the arc length, which seems like a strange thing. But parameterizing in terms of the arc length is really nice.
So give you like a system that's like your gradients set out for whatever.
So sort of. So what parameterizing in terms of arc length does is makes the things that you work with on the curve a property of the curve, not a property of the parameter. Right. All right. So we have y equals 1 minus x squared. So we want to find a set of parametric equations. Is that the example I want to do? No, I'm going to change my example. Y equals x cubed plus 5. With it's just different. With the parameter x equals t. Well, what's our first of our pair of parametric equations? X equals t. That's one equation. And then the second one, y equals t cubed plus 5.
Good job, Kevin.
And if we graph this, what does the graph of this thing look like? It's just a cubic, but what does the 5 do? Shifts it up 5. So we're going to have something like that. And with this parameterization, what would be the orientation?
Left to right.
Left to right. As t increases, x increases.
This function is not a
No, this is not just a way to represent this as a set of parametric equations. How would we change this? How would we change this, folks? Listen up. How would we change this and get a right to left orientation? X equals negative t. Just go the other direction. What if we wanted to parameterize this in terms of the slope? So for some reason, we want to parameterize this curve in terms of the slope. So what we would do is we would know the slope. We would plug the slope into x and y and get our coordinates. So say we know the slope at various points, and we want the x coordinate and the y coordinate. So we need to take the derivative. I'm going to say, we'll call the slope m as a parameter. Well, m is dy dx, right? So we take the derivative of this, equals 3x squared. So x, in terms of the slope, x equals the square root of m over 3. That would be our x-coordinate in terms of the slope. So if we knew the slope we plug the slope in, and we get the x-coordinate. And the y-coordinate, y equals x cubed plus 5, the square root of m over 3 cubed plus 5. So we could write that as y equals m over 3 to 3 halves plus 5. And for any particular value of the slope, we could figure out our x-coordinate and our y-coordinate on that curve. I'm not sure why we would parameterize in terms of the slope, but this is kind of a precursor to when we do parameterize in terms of the arc length, which doesn't seem like a particularly intuitive parameterization, but it's a very useful parameterization. Now I did we can represent one reason that we use parametric equations is there are curves that are extremely difficult to represent in explicit form. And one of those is a cycloid.
What? A cycloid, Dylan?
So what a cycloid is if you visualize, for example, a light on your bicycle wheel. So there's a light on the edge of your bicycle wheel. As your wheel goes along, the path of that thing is this path called a cycloid. And it is difficult to represent the equation of a cycloid in explicit form. I'll show you what it is in parametric form. We get x equals a theta minus sine theta, and y equals a1 minus cosine theta, where the radius equals a, and theta is the angle through which the circle is rotated. So you say theta equals 0 when pick a particular point on your bicycle wheel when it's horizontal. Theta equals pi, theta equals pi over 2. Theta equals pi. So as the point on your wheel rotates, your parameter is the angle through which it has rotated. I did a video, relatively short video, where I derive these parametric equations of a cycloid. So I should go through the process of showing you how you would come up with these parametric equations. So I would encourage you to look on my YouTube channel. And look at that derivation of the parametric equation of a cycloid. It gives an example of how we come up with some of these how you would come up with this set of parametric equations. Now, what I want to do next, before I give you the homework, is there's a website, and it does animations of the cycloid and some other parametric curves, and I think it's really fun. Mm-hmm. So a cycloid could be kind of like a rectified AC current.
Yeah,
You flip the negative up. Yeah.
In radio, when you parameterize things for sine waves,
Right?
And you have to use parametric, right? You can't do it the other way. It's complicated. This is very simple. Your computer can handle this. But if you give it in a rectangular, it can't handle that. That's bad.
Can you stop?
And I'm going to stop this.